Hello and welcome to another episode from Spiral Physics Education. So we're going to be looking at Sankey diagrams in this lesson, and we're going to look at how to use them and their link to the principle of conservation of energy. We'll be looking at how to complete Sankey diagrams, also how to use them to calculate efficiency, and then finally how to complete them using scale diagrams. So what is it that you need to know for this lesson? Well, once again, for this, you need to know about stores and transfers, energy stores and energy transfers, the principle of conservation of energy, efficiency, the definitions of work, energy and power, and also about energy transfer diagrams. And if you're uncertain about any of those, don't forget to check out other videos on the channel to help you get up to speed on those before looking at Sankey diagrams. So Sankey diagrams then. What are they? Well, these are tools that are used not only in physics but in engineering to illustrate energy transfers, and it also helps us look at the efficiency of a device. And they end up looking something like this in its most basic form. And the sizes of these arrows are very important. So this on the left hand side here represents the input energy. So the bigger, the thicker that beginning of the arrows, the more or the larger the input energy is. And what we usually use is this arrow that carries straight on is the useful energy output, and you can see that its thickness is much smaller than the input energy, and that's we can use the thicknesses to compare the energy values. So if the useful energy output was a third of the input energy, then we could say it's actually 33% efficient, for example, but the thicknesses are vital. So the arrow that goes down, we refer to those as the wasted energy, whatever forms or transfers or stores they are. And the thickness of that arrow here across the arrowhead is the same as that thickness there. So the total energy is equal to the useful energy plus the wasted energy, and all of those thicknesses, those two thicknesses add up to the input energy thickness all the way around. So let's start off with an example. And here we've got our basic setup for our first Sankey diagram. And it's an incomplete Sankey diagram for a filament bulb. And what we're going to do is we're going to complete it by identifying the missing energy transfers. So for this bulb, what we've got to firstly look at is what the input energy is going to be, and that's going to be electrical energy. So electrical energy is going into the bulb. And then what is the useful energy coming out? So if we're thinking about the useful energy coming out, well, we'd call that radiation energy transfer, or we could say light energy. So that's being transferred usefully from the light bulb. Then the wasted down at the bottom is going to be a thermal energy transfer. Remember, that would be to the surroundings, and it would be dissipated to the surroundings. So let's try another example, and we're looking for this Sankey diagram to work out how much light energy is transferred away from the light bulb. So we've got 100 joules of useful electrical energy being transferred to the light bulb, and we've got 85 joules is being wasted or dissipated to the surroundings in the form of thermal energy transfer. And what we're trying to do is work out what's going to be useful energy transfer. And it's just the difference, so 100 minus 85 will tell us that 15 joules is transferred usefully in the form of radiation energy or light, if you prefer. And what we can do with that, we can then use the equation efficiency to calculate how efficient the light bulb is. So remember, that's from one of the other videos, is that the useful energy output divided by total energy input. Well, the useful energy output is 15 divided by 100 it's 0.515 efficient or 15% efficient. Okay, let's have a look at a third example. So this time we're going to look at an energy saving light bulb, and it's going to be 25% efficient. And we're going to complete the Sankey diagram by calculating the missing energy values. So we've got the input energy, the electrical energy input is 1200 joules, and we're told that it's 25% efficient, which means that we can work out how much useful energy is transferred into radiation energy or light. So that's going to be 25% of 1200, which is 300 joules. That means that we've got 900 joules that is wasted. Okay, so this is the last example. Sometimes you can get exam questions where there is a grid, and what we're going to use for this example here is a scale to calculate the missing energy values for the Sankey diagrams on the TV. So the first thing is we've given the electrical energy transfer for the TV is 240 joules, and we're told that there is two different types of useful energy transfer. There's radiation energy transfer in the form of sound and also in the form of light. And down at the bottom it's told us that there's a thermal energy transfer is wasted to the surroundings, but we don't know how much. We're only told that the electrical energy transfer is 240 joules. So we're going to have to use a scale. So if we look here, we've got 12 squares, and those 12 squares represent 240 joules. And that means that one square is therefore equal to 20 joules. So we've got to apply that scale to everything else. So let's have a look at the radiation energy transfer in the form of sound. So it's got two squares. So two squares, if one square is 20 joules, then two squares is going to be 40 joules. And now let's have a look at the radiation energy transfer in the form of light. So that's that thickness of arrow there, and that's 6 squares. If one square is 20 joules, then 6 squares is 120 joules. So we've got 120 joules of radiation energy transfer in the form of light. So let's see how much thermal energy is transferred or dissipated to the surroundings. So that's that thickness there. So we've got 4 squares. So one square is 20 joules, and 4 squares is therefore 80 joules. And we can do a quick mental check. Here we've got 240 joules being transferred to our TV. 40 in terms of sound, 120 comes out in terms of light, and 80 is wasted. So you can see there that all of the energy transfers from the TV add up to 240 joules, and there's 240 joules being transferred to the TV. So quick mental check, everything seems to be all right on that. So that's it for Sankey diagrams. I hope you found that useful. Don't forget to subscribe to the channel, and I will see you next time on Spiral Physics Education. Goodbye.